Okay, let's go ahead and get started today. And I'll tell you from my personal perspective, it's been one of those days. You know, between dogs not coming in when they're supposed to and losing keys and technology not doing what it's supposed to do. Yes. It feels like a Monday. Yeah. So I was trying to post a test into eLearn for the AP2 class. It should have taken 15 minutes. I would just finished it before you walked in. It took me an hour and a half. There's a lot of starts and stops. So it's been, I have no expectations on how today's going to go. So anything good that happens is great. So anything that just, even if we are average today, it's better than it's been so far. So, okay. There is no lab test this week. It's next week. Lab today and tomorrow. We will take a look at the cheek cells. We finally did that yesterday. And I finally realized I can't put 3 weeks worth of lab into 2 weeks. It just doesn't work, no matter how hard I try. So lab today will be, I'll talk about cells and mitosis and cell division. We'll do the cheek cells. And yesterday we had plenty of time, so I went ahead and started talking about the bones of the skull. Now, I should have said this yesterday, but I'll say it now. The bones, anything on bones is not on the first test. The first test is only what we've done the first 2 weeks plus what we do today, except for the skull. The bone test is a separate test entirely. It's weeks away. So don't worry about that. But the more we talk about bones, the sooner you can start thinking about them. So, okay, anybody have any questions on anything? So, hey, how about Ohio State? They win and they still drop in the polls. Yeah, sorry, I just couldn't resist that. Okay, let's go ahead and get into where we were. We're talking about chemistry. And let me bring this up. Everybody should see the slides of chemistry. And here we go.
My attention down to the subject. Get it
Oh,
down.
that was good. Horrible, but good. So, okay. So up until now, we've been talking about solutions and mixtures and stuff like that. You know, a mixture, of course, is when you simply put several ingredients together to produce something. The something that you make doesn't change the properties of the components. If you make chocolate milk or sweet tea, you can still filter out the chocolate in the chocolate milk. You can still filter out the sugar in the sweet tea. There's no chemical change to either one of the ingredients. Even the salt water, which we used last week in those artificial cells, the salt in here is still salt. The water is still water. I could filter out all the salt. There's no chemical change to the salt when it's in the water. It has not changed its properties. It's still salt. The water is still water. There's no change to it. We've done nothing to it. Now, and that's, physical combinations are like that. We're going to talk about some chemical combinations. Now we're going to talk about chemical bonds. And this really does deal with electrons. And now there's a reason we talk about electrons in here. It's not because I really like electrons and I'm a frustrated chemistry professor. It's the furthest thing from the truth. The only reason we talk about electrons is because that's where energy gets stored in chemical bonds. You can't see a chemical bond, you can't really touch it or feel it. But what happens in a chemical bond, something takes place with the electrons. We steal electrons from one atom to another, or we share electrons, or we're just sort of attracted to other atoms by almost like magnetism. We're going to do something with those electrons, because those electrons usually have a certain amount of potential energy. Remember what potential energy is. It's the energy at rest. It's stored energy. You know, like we charge our phone. We've got stored energy in there. We can use our phone all day. We, you know, your laptops, your tablets, whatever you're using is stored energy. You have it all stored in there. You're running on that. You know, who hasn't been, I've got 2 minutes left on my phone. I'm at 2%. I better finish up, or I better talk really, really fast, or whatever, you know, or send this text really quick. But we, you know, and you know, I know that when your laptop dies, I mean, it just, you know, it gives you that warning, and as soon as the warning goes out, mine goes, you know, that wasn't a warning, you know, that was a deadline. But the electrons play a role in all that energy. The food that we eat, you know, whatever you're eating or drinking today, that has calories in it. The energy that we measure in calories comes from the electrons in the molecules of the food, like sugar, glucose, table sugar, sucrose, carbohydrates, the starches. If you had a donut or an apple or a banana or a bowl of cereal or anything today, even if you didn't eat anything, the energy in that food comes from the electrons in the molecules of the carbohydrates, the starches, which become sugars, or the proteins or the fats. And so that's why we pay attention to the electrons, not because we're so, oh, this is a chemical reaction that we really like to talk about. You know, our bodies are all chemical anyway, but the reason we look at electrons is because of their potential energy that we use. Okay. If you're an atom, you've got electrons. Even if you're a hydrogen atom, you've got one electron. In the periodic table up there, number 1 on the far left at the top left-hand side, the letter H, there's a red 1 above it. That means it has 1 proton and 1 electron. And that electron is attached, is held in place by the positive force of the proton in the nucleus of the hydrogen atom. In fact, the nucleus of the hydrogen atom is just a proton. You know, it, with apologies to everybody online, here is a hydrogen atom. There's the proton. Here's the electron. It's in orbit around the proton. The proton is the nucleus in that case. Now that orbit is called a shell. And we're going to use a term, or I'll use a term, shells and orbitals around the nucleus. I'll use them all interchangeably. All I'm talking about is that this first shell, this first orbital, is usually a set distance away from the nucleus. The energy in that electron is fighting the pull of the proton. The proton, it's like a magnet. Positive charge here, negative charge here. You know, this is probably like 10 billion times bigger than in mass than this, but the charges are the same. And so this electron is using most of its energy, most of its kinetic energy, to stay away, to not be pulled into the proton. Yeah.
That's what you would consider the planetary model, right?
That's the planetary model.
I was just making try to get to.
Yeah. See, I like the planetary model because it's easy to explain how it looks. You know, we don't care about the big electron cloud. We're not chemists. We're not teaching chemistry. It's easier to explain where the electron is if you use the planetary model. So but the reality, of course, is it's a big fuzzy ball, you know, because the electrons are moving so fast. Anyway, that's our first shell. It also refers to a certain level of energy. So an electron in the first shell has a little bit of potential energy left over because it's not using everything to keep from being pulled in, but it could be, you know. Now, most atoms have at least 2 shells. around it. I just made helium. 2 protons, 2 electrons. Goes in its first shell. So now we have 2 electrons in the first shell. Let's make what's next? Lithium. 3 electrons. The first shell can only ever hold 2. Shell 1 holds only 2 electrons. No more than 2 electrons. That's, so, and to have 2 electrons, you have to have 2 protons. The only atom that holds 2 electrons in its first shell and nothing else is helium, because helium has atomic number 2, 2 protons, 2 electrons. The second shell can hold up to 8. Doesn't have to hold 8. Lithium only has 3 protons, so it's only going to have lithium. It's only going to have 3 protons and 3 electrons. The first shell will only ever hold 2. And that works for every atom except hydrogen, which only has 1 electron. So you have lithium there with 2, and you have 1 in its third shell, but it can hold 7 more. Second shell can hold up to 8. Third shell can hold up to 8 or 18, it depends. Now there's 7 different shells. We don't really pay attention after the first 3, because the atoms that we deal with in the body, we don't tend to get past the 4th row across there. And we pay, from number 19 over to 36 is about as far as we go. So we don't have a lot of, we don't have to generally worry about that third shell very much. Very few atoms that we deal with go past that third shell. So the further out you are from the nucleus, the more potential energy you contain. So hydrogen contains a little potential energy. Carbon contains more potential energy in its electrons. Potassium has even more. The bigger the atom, the further out the electrons are, the less they're being pulled by the nucleus, the more potential energy they're going to hold on to. So, and that potential energy is something that we measure in our food. The calories, like in your Dr. Pepper, or it's not labeled on yours. Yeah. But yesterday, everybody was eating Fritos. That's not the whole side of that room. Yesterday was eating Fritos. Like the calories were just like, oh, what are your calories? What are your calories today? It's like your Dr. Pepper was what, 240 calories or something?
Something like that.
Yeah.
210.
210. Okay. 210 calories of energy in that Dr. Pepper. How do we calculate it? Well, we don't have to calculate it, but it's already done. It's that those calories are based on the number of electrons in the food molecules in the Dr. Pepper, usually the sugars, the sweeteners, and their relationship with, its carbons and hydrogens and the electrons spinning around each other, and how much potential energy is available. And so you can look at that Dr. Pepper and say, well, that represents 210 calories of potential energy I can use later on. And then if you start talking about electrons, all your friends are going to gradually walk away real fast, because nobody wants to hear about electrons in their Dr. Pepper. So,
Sounds like bugs. I think you got bugs in your drink.
oh yeah. So yeah, if you end up in science, you definitely know how to clean out a room real fast, of people. So okay, now let's back to where I was. Okay, there we go. Now, okay, this is what an electron looks like. This is a good example of the planetary model here. This is a great little animation. This is aluminum. And one of the best things we use aluminum for, aluminum salts. We find aluminum salts in our antiperspirants. It's what we have in our deodorants. It doesn't hide the odor, but it blocks the pores in the axillary region where we have a lot of sweat glands. And so when we use an antiperspirant, we don't sweat because the aluminum salts block the pores. That's a major improvement in deodorants. Anyway, we have aluminum here. We have the nucleus with the protons and the neutrons. Protons are positively charged, neutrons are neutral. We have 13 protons and we have 13 electrons. We have 2 electrons in our first shell, and we have 8 in our second shell, and we have 3 in our third shell. We have 2 in the first shell, 8 in the second shell, and 3 in the third shell. So we have an atomic number of 13. The protons and the electrons are balanced. We know we can have 2 electrons in our first shell. We know we can always have up to 8 electrons in the second shell. The third shell will hold up to 18, depending on the atom. In this case, it only holds 3. That's the outer shell of aluminum. We call it the valence shell. The valence shell electrons, the outer shell electrons, always have the greatest amount of potential energy. They're the ones we work with in our foods. We don't think about it, but that's where the energy is coming from. The calories in our drinks, and the calories in our food, the fats and the carbohydrates and the proteins that we consume all have a certain amount of potential energy. It's all added up in the calorie makeup in the drinks. Somewhere, all these food groups got tested. There's a device that will, it's constantly being, foods are constantly being evaluated, and you can actually measure the amount of energy released from a Dr. Pepper, an apple, a banana, a Whopper, chicken wings, whatever. So we know when we see the food labels, we know exactly, more or less, how many calories we're getting out of that. Okay, the valence electrons are the electrons that we use when we have a chemical reaction. When we have a chemical reaction. We have chemical reactions take place all the time in our bodies. We're always converting carbohydrates. We're converting starches into sugars, simple sugars, and then converting those sugars into carbon dioxide and water. Ultimately, everything that we drink ends up as energy and carbon dioxide and water. And of course, the stuff that we can't process comes out as waste material. Okay, now, so we have, this is what our electrons look like. Now, we're interested in chemical reactions. A chemical reaction, meaning lighting a match, is a chemical reaction. Starting your car and converting the fuel in the car to the potential energy in the gas tank, converting that to mechanical energy is a chemical reaction. You ignite the fuel inside the engine, hopefully only inside the engine, but you ignite the fuel in the engine, and the engine then generates mechanical energy to turn the drive wheels, and you go forward or backwards or whichever way you're going to move the car. Those are all chemical reactions taking place. So whether it's in our bodies or outside our bodies, we're going to be using these electrons. We're going to be using these electrons in any kind of chemical reaction. So the problem with the atoms is atoms want to be stable. They want to have their outermost shell always filled up. Whether their valence shell is like hydrogen with just one shell and one electron, or sodium with its valence, with its atomic number of 11, with 2 electrons in its first shell, 8 in its second shell, and 1 in its third shell to give it 11. All these atoms want to be stable. They want to have their valence shell filled up with electrons. Everybody wants to have a full shell. The problem is that only a handful of atoms have full electron shells. The ones on the right-hand side there under the number 18, those are called the noble gases. There are things like helium, which we talked about. You know, helium has all sorts of interesting properties, not the least of which is lets us talk like Donald Duck. You know, it alters the way the vocal cords vibrate. Helium and neon. We use neon for lighting. We use argon and krypton as gases in fire suppression and in insulation and glass and things like that, but they are all non-reactive. Those atoms can't react. Their valence shell is full. The reason atoms react is that they want to grab other electrons to put into their valence shell so they're stable. Hydrogen only has one electron in its outer shell, its only shell. Elemental hydrogen is reactive because it's trying to get another electron. It wants to be happy. It's not happy right now. And elemental hydrogen is very reactive. You know, the Germans learned that a long time ago when they used to make their big blimps and fill them with hydrogen gas instead of helium. And hydrogen gas is very reactive. And you get one little spark and you have a complete disaster. The Americans used helium. We still use helium in our blimps. You know, if you watched any football over the weekend and you saw one of the blimps, you know, usually the Goodyear blimp, but there are you know, I think MetLife is flying over the US Open or something like that, but they're all filled with helium. Helium doesn't ignite. Helium doesn't react with anything. It's very safe. So the driver for these chemical reactions is for all these atoms that are not stable to become stable. The only ones that are stable are the ones on the far right-hand side. And we can't do a whole lot with helium and neon, argon and krypton for our food. Doesn't, you know, it's not going to do a whole lot for us. So if you're an atom, you want to gain electrons or lose electrons to reach some form of stability. So, and there are those inert elements, helium and neon. You see helium has atomic number 2 protons and 2 electrons. Neon has an atomic number of 10. It has 10 protons, 10 electrons, 2 in its first shell and 8 in its second shell. Helium and neon and all the rest in that column don't react with anything. You can't get helium to react with oxygen or with water or with carbon. It won't, it's non-reactive material. That's why it's great for fire suppression, for example, because, you know, there's nothing in it can't ignite or do anything. Good question. Just stretching. Okay. So, now that I've embarrassed you, I'm sorry. So, okay. Now, these are the reactive elements. I just picked on hydrogen, but look at carbon. Carbon has an atomic number of 6. It has 2 electrons in its first shell and 4 in its second shell, and it would dearly love to have 4 more. So carbon reacts with lots of things, usually hydrogen. Hydrogen combines with carbon all the time. That's where the term carbohydrates comes from. The carbs that we pay attention to in our foods, the starches and the sugars are the carbohydrates because they're made from carbons and hydrogens and oxygens. The oxygens where it gets left off the name, but it's still carbohydrates. And there's a lot of energy when you available when you combine carbons and hydrogens. Oxygen, throw that into the mix. Oxygen has an atomic number of 8, 2 protons in the first shell, 6 in the second shell, and it still wants to get 2 more, so it'll have 8 in its second shell. Oxygen is reactive. It wants to combine with something else. And the same thing with sodium. Sodium has a very easy solution to its problem. Sodium has an atomic number of 11. 2 electrons in the first shell, 8 in the second shell, 1 in the third shell, And that third shell electron all by itself tends to get kicked out by sodium. Sodium, instead of combining with somebody else, sodium will kick it out. And now it's stable. And most of the sodium in our bodies is that vert form where we have one less electron. So we have three types of chemical bonds. It's going to come back to that sodium here in a second. Ionic bonds, covalent bonds, and hydrogen bonds. Now, ionic bonds are a type of chemical bond that involves physically moving electrons from one atom to another so that we get stability. Atoms gain or lose electrons. If an atom gains electrons, it's called an cation. It's positively charged. I'm sorry, if it gains electron, it's an anion. It is negatively charged. If an atom loses an electron, it's now a cation and it's positively charged. Now, if you are an ionic compound, you're a salt. Most of our salts in the bodies are going to be formed from ions. They form crystals, these ionic bonds, like sodium chloride, table salt. That's an ionic bond. You have combined sodium and chlorine. You have calcium carbonate. You have magnesium chloride. You have potassium chloride. All of these various salts in our bodies. You see a lot of chlorine in here too, but all of these salts in our bodies are held together as ionic bonds. They form crystals. Now, crystal has a very specific structure. Notice how the crystal forms a very specific lattice-like arrangement where we alternate between in this case, the sodium and the chlorine, back and forth like this. A very consistent arrangement. This is how it always looks, where the atoms are lined up like this. And most salt crystals, depending on whatever salt it is, are going to look the same way. And so all the salts that our bodies use, and it's mostly sodium chloride, but there are other salts in there, are going to look like this if they're not in solution. Now, how do we get to an ionic compound? How does it form? Well, this first approach to making a bond is the actual physical transfer of an electron from one atom to another. If you gain an electron, you develop a negative charge. You're no longer called an atom, you're called an ion. In this case, an anion, like the anode end on a car battery. You know, the negative end, the negative post, the black post, and then you have the red post, the positive end. That's the cation. You know, when you jump your car, you know, you have to put red to red, black to black, because if you don't do that, you'll have, you know, it won't work. That's the best thing I can say. Now, if an atom gains an electron, it's negative, because atoms are normally balanced. If you have 10 protons and 10 electrons, and you get another electron, you now have 10 protons and 11 electrons, you're negative. But if you have 10 protons and 10 electrons and lose an electron, now you still have 10 protons with only 9 electrons, you're positive. You now have a positive charge. So we don't call them atoms anymore, we call them ions. We generally say the positive ion and the negative ion. You know, you can say anion and cation, but we generally say just the positive and negative. Now, what's the most important set of ions in our body? Sodium and potassium. Now, they're both positively charged. But our cells are organized with lots of sodium on the outside and lots of potassium on the inside. The inside of the cell tends to be negative, with respect to the outside. Just take that at face value right now. I'm not going to try and explain how a positive potassium can become negative. We'll get into that later on. We get into muscles. And it'll make more sense. But all of our muscle cells, all of our nerve cells, all have lots of sodium ions on their outside. They're all positively charged. And they have a lesser amount of potassium ions on the inside. Potassium is still also a positive, but there's less of them. So the inside of our cells tend to be negative with respect to the outside. Okay. They're anions. I mean, they're cations. Now, chlorine is an anion. It's negative. Chlorine is the primary ion inside our cells, but it doesn't do anything for us. You know, sodium chloride is table salt, but the chlorine just sort of gets to watch. It's not a very important ion. And we'll see that in AP2, that all the heavy lifting in our bodies is done by the sodiums and the potassiums and the calciums, and the chlorine just doesn't, it's there, but it doesn't do a whole lot for us. You know, chlorine's not one of those, you know, nobody gets too worried about our chlorine levels in our plasma. We pay attention to sodium and potassium and calcium and stuff like that. Okay. Now, how do these come together? Well, if you're an atom and you give up an electron, you have a positive charge. And another atom grabs an electron, it's now got a negative charge because it's got more electrons than it was supposed to have. They come together like magnets. It's called an electrostatic attraction. It's called an ionic bond. It's a very weak bond. It holds these atoms together, these ions together, but it's not a very strong bond. But it works. Salt crystals look like salt crystals. I've got salt crystals on the bottom of this beaker. You know, they're held together. You can see them in the beaker here. They're held together by electrostatic attraction. Now, if you want to know what electrostatic attraction is, anybody know what a Swiffer is? Who hasn't used, who's used a Swiffer? You know what a Swiffer is? So, right. Beautiful marketing approach. Use the Swiffer to clean the floor up. We all know that first cloth fills up with crud in like 3 passes, and then you got to get another one, and then you got to get another one, right? And it works, but it fills up with dirt. It does such a good job that you can't use it very long. The reason that works is because the cloth, as you rub it across the floor, generates a charge. And that charge is either positive or negative to the dirt on the floor. And so the debris, the crud, is attracted to the cloth, just like these atoms are attracted, these ions are attracted to each other. It's like a magnet. And that's why those cloths do such a good job. The problem with them is that if your house is really dirty, you're not gonna, or if you got dogs and cats, you're not gonna get a lot of use out of one cloth because of this electrostatic attraction. So this is how our salt works. Same way, they're attracted like magnets. So now this shows you what happens. Sodium wants to get stable. It doesn't like that third shell with the electron out there, so it will kick it out. And now sodium's happy. Its outer shell is filled up. It has a positive charge, but its outer shell is filled up because it now has 11 electrons and only 11 protons and only 10 electrons, but its outer shell is full, so it's happy. Chlorine tends to grab that electron because chlorine's outer shell has 7. Chlorine has 17 protons and 17 electrons. Its outer shell, the first shell is 2, the second shell is 8, the third shell is 7, it has 17. It would love to have one more electron in its outer shell to be stable. And so it grabs that electron from sodium. And now we have 18 electrons. 17 protons, 18 electrons. Chlorine is negative because of the extra electron. Sodium is positive because it lost that electron. And now these ions are attracted to each other. And we form the crystal, which is a very weak bond because it breaks apart in water very easily. You know, what happens when you add water to salt? The salt dissolves. You know, it breaks apart very easily. Consider sugar. What happens if you put sugar into water? What's going to happen to the sugar?
Dissolves.
Eventually, you know, if you have iced tea and you add sugar to cold iced tea, what's going to happen? You're going to get sludge at the bottom, right? You know, and you're going to have to stir it and stir it and stir it. My grandma used to love a little tea with her sugar. You know, she'd have about that much sugar sludge at the bottom of her tea, you know, because she'd just keep adding to it. But the reason is that sugar isn't held together with ionic bonds. Sugar has a different type of chemical bond, and it's harder for those bonds to break. And so you have to stir and stir and stir to, you know, now we beat that by dumping sugar into the hot tea first. So that's how, you know, everybody knows how we make sweet tea. So, okay. The big one is the covalent bond. We don't steal electrons. We don't pick out electrons with this. We share them. We share electrons. The valence shells of atoms can share the electrons. And since the electrons are moving so fast, they can be around one atom and then around another atom. And as far as we're concerned, it's at both shells are filled up because they're moving so rapidly that they're in both places at the same time. Because if you're moving at 186,000 miles per second, the speed of light, essentially, and you're traveling from valence shell to valence shell and spinning around rapidly, you can't measure it, you know. So essentially, we are seeing the valence shells of all the atoms involved here filled up at least part of the time, and that keeps the atoms stable. So a covalent bond occurs when we share electrons, and most things of interest in the human body as far as chemicals and molecules go are held together with covalent bonds. So we're at least part of the time we're filling up the valence shell, the atoms are happy. And this is the most common type of chemical bond. We usually have single bonds. Most sharing of electrons is a single bond where you're just sharing 2 electrons. In some cases, we share 4 electrons. That's a double bond. Elemental oxygen isn't used by our bodies to breathe. We can't survive off of elemental oxygen, the one on the periodic table there with the atomic number of 8, because we breathe O2. Atmospheric oxygen is 2 oxygen atoms held together with a double bond. It's very, very stable. It fills up all of its spaces, and we breathe this stuff. Atmospheric oxygen is much less reactive than elemental oxygen because all of its valence shell spaces are full. 6 electrons, a triple bond. We don't have a lot of things with triple bonds in them. Nitrogen, atmospheric nitrogen, the stuff that makes up about 79% of our atmosphere, is held together. The atoms are held together with triple bonds. So the nitrogen molecules are extremely stable. They don't react with anything. We don't really use the nitrogen gas for anything when we breathe, but it's a very stable environment for us. So this valence shell bonding allows each atom to, for part of the time, to have their shell filled up. So this is a covalent bond. Up here in the upper right side, we see these are two atoms of hydrogen. Each hydrogen brings along one electron. When they share their individual electrons together, we now create H2, atmospheric hydrogen. And at any point in time, the electrons are moving so rapidly that they are satisfying both atoms need to have two electrons in its valence shell. Because that's extraordinarily slow as far as the atom's concerned. But if you could take a snapshot, you could see at any point in time here, the right side has two electrons and the left side has two electrons simply because they're moving so fast. The H2, atmospheric hydrogen, doesn't react. It's not going to combine with anything else because it's very stable. It's all because they're sharing their electrons. We see down at the bottom, we see hydrogen and oxygen sharing electrons. Hydrogen still has its one electron. Hydrogen still has its 6 electrons in its outer shell. Hydrogen wants to get up to 8. And oxygen wants to get to 8 and hydrogen wants to get to 2. And so the oxygen supplies an electron for the hydrogen to share, and the hydrogen provides an electron for the oxygen to share. And so they combine. And it is a painless way for the atoms to share their electrons and achieve the stability in their valence shell that they want to get. Atoms love to fill up their valence shell one way or another. Here's a good example. Carbon has an atomic number of 6. 6 protons, 6 electrons. 2 electrons in its first shell, 4 in its valence shell. Carbon is reactive, and it usually combines with hydrogen because a carbon atom can satisfy 4 hydrogens by sharing electrons. At the same time, 4 hydrogens satisfy the carbon by giving it 4 electrons to share. And so now we get one carbon atom surrounded by 4 hydrogens. We now have created methane gas. Methane also called natural gas, is based off of, this is a carbon atom right here with 6 protons, 2 electrons in the first shell, and 1, 2, 3, 4 electrons in the second shell, and it will combine with 4 hydrogens. And now we have 1, 2, 3, 4, 5, 6, 7, 8. The hydrogens are happy because they get their 2 electrons. The carbon's happy because it gets its 8 electrons in its valence shell. Natural gas, methane. Now, what is the advantage of having all these electrons floating together in methane? What do we use methane for?
Ignition.
Ignition, okay. Anybody have natural gas in their house? You've got gas? Is it natural gas or propane? Propane, okay, that's even better. So, anybody have gas? For heat, yes, natural gas for heat. We heat our homes with natural gas. We cook on natural gas. Some cars are powered on natural gas. The utility, SCUD, the local utility district, has trucks that run on natural gas. And I think Dollywood has, I think, their trolleys.
There's a few school buses.
Yes, there are a few school buses that run on natural gas. So they're powered by methane. And because there's a lot of potential energy. All these electrons here represent a lot of potential energy. So we burn this stuff and we release that energy. We can do things with it, we can cook with it, we can heat our houses with it, we can run our hot water heater with it, we can heat our clothes dryers, power our clothes dryers with it, and do all sorts of stuff with it. So we use natural gas all the time. Now you said you have propane. Propane's even better because propane is, instead of having one carbon atom, has three. This is propane, 3 carbons, and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Propane is even more efficient. There's more energy in propane. What do we use propane for besides heating our houses? Do you ever grill? Yes, thank you, yes. Gas grill. If you got a gas grill, you got that little tank of propane, that when it gets empty, you go down to Walmart or Home Depot and get a refill, right? And you cook with it. Well, in larger tanks, you heat your house with it. Heat your hot water with it. We can power our vehicles with propane. There are propane powered vehicles too, because there's more energy. Again, the energy of from the valence electrons in that molecule. And we can't get any energy out of that by, we can't breathe propane and get energy, but there is a great deal of potential energy stored in that propane. And by igniting it, we can use it. We can release the heat to do things simply because of all the electrons in there. All of those electrons represent a lot of potential energy. And so that's, this is, and while we don't think of it as a carbohydrate because there's no oxygen involved here, it is a combination of carbons and hydrogens. A great deal of potential energy stored there. All because of those electrons that are just far enough away from the nucleus to have an adequate amount of potential energy that we can use. Same thing applies to gasoline or diesel. The electrons in the molecules of those fuels are going to, when we burn them, we're going to release that stored energy in the gasoline or in the diesel. Now, a couple of observations here. Most of our molecules are going to line up. Some are going to be in a straight line. Some are going to be in a sort of like a circular shape. Some are going to be sort of at a 45-degree angle to each other. Different molecules take different shapes. Now, carbon dioxide is a good example here. This is a covalent bond between the oxygens and the carbon. Carbon dioxide is generally non-reactive with a lot of things. It is balanced because it has an oxygen on each side of the carbon with a double bond. It doesn't have, one side of the molecule doesn't have any charge different than the other side. We call it a non-polar covalent bond. Oh, thank you. Okay. Non-polar covalent bonds, meaning that they are electrically balanced. They don't have any, one side of the molecule is no more positive or negative than the other side. The electrons are evenly distributed. Now, carbon dioxide is pretty neutral. It doesn't do a whole lot. There's nothing there for it to react with and other things. So, in fact, our bodies generate a lot of carbon dioxide and we just breathe it out. However, there is something called the polar covalent bond, meaning it has a positive and a negative charge on it, or a positive and negative end. A polar covalent bond occurs when you have an unequal sharing of the electrons. And so you change the shape of your molecule. And while it doesn't sound like a big deal, it does become pretty important to us when we consider water. Now, water has a very unique shape to it. Water is shaped sort of like Mickey Mouse. You all know what Mickey Mouse looks like, right? This is my Mickey Mouse. That's Mickey Mouse. Okay. Now, but this is also a water molecule. Hydrogen, hydrogen, oxygen. Because there is unequal sharing of the electrons in here, we create a slight positive and a slight negative end of a water molecule. All water molecules look like this. All water molecules are slightly positive here and slightly negative here. It's time you get this to look, a water molecule, you know. So anyway, because of this unequal sharing of electrons, we create poles, positive poles and negative poles. The water being a polar molecule, what happens with water is that oxygen has 8 protons down here in the nucleus. There's 8 protons. And they create a pretty strong pull on all the electrons. And so hydrogen has contributed 1 electron each there and there. And those electrons are attracted to that very powerful nucleus. Yes, the charges are balanced. You have an electron and a proton are balanced electrically, as far as the charges go, positive versus negative. But you have 8 protons together right here in the nucleus of the oxygen, and it tends to pull this electron down a little further like that. Same thing over in this side. So what we end up with is all the electrons all the way around being pulled down this way. Not just the 2 from the hydrogen, but the 8 electrons from the oxygen itself. So we end up with 10 electrons, in sort of an oblong, pattern like that, circling the nucleus. And so that those 10 electrons tend to make this end slightly negative. And since you're pulling the electrons away from the hydrogens, the protons tend to make this end slightly positive. Now they don't lose those electrons. The nucleus of the oxygen never wins. It just bends the orbit of those electrons so that they tend to be pulled towards the one end of the molecule. So you have all these electrons down here. So what does that mean for us? It means that water attracts itself like this. This is a water molecule, positive, positive, negative. Here's another water molecule right here, positive, positive, negative. This end is attracted to that. And over here's another water molecule. And this end is attracted like that. And then we go like that, we go like that. And pretty soon we have a great big network of water molecules.
Is that what gives them their like semi-solid property? Where
Exactly. It's why if you splash a little water up in the side of this, the water sticks together. If I pour water out on the desk, it's going to form a puddle. The water molecules are sticking together. They have great attraction to each other. It gives them their properties. This is why ice will float, because when ice floats, it freezes in this same, when water freezes, it excuse me, it freezes in this lattice work arrangement, and air fills up the spaces. So it is less dense than water, and it floats. We know what ice is. We see ice all the time. But ice will float on top of the water because the air trapped inside, simply because the water molecules are polar and they attract each other with these little weak bonds. And these are called polar bonds. And the bond that are holding them together are called hydrogen bonds. It's a very weak bond. They break and form and break and form all the time. So the negative end of one atom is attracted to the positive end of another atom.
It's basically like rolling a bunch of magnetic balls around.
Yes, positive and negatives are attracted to each other. And with water, it always forms the same shape. It always forms this lattice work structure. You know, you look at lattice like underneath the deck or something, that's exactly what water molecules organize themselves in. It's how they can form a drop. It's how, you know, you see a drop on the side of your cup, your glass, whatever, where you see a puddle, how the water is holding together. The water will always hold itself together and reform back into this shape there and just spread out all through these weak bonds. They break, they form, they break again. And this is really important to us in our bodies because we like to keep our water, you know, we don't like our water molecules to go flying off individually. We use our water in our bodies for insulation and for cooling and for transport. There's all sorts of things we need water for. And we like the fact that the water is a medium, if you will. So, okay, so these are hydrogen bonds. They're very weak, but without hydrogen bonds, we wouldn't have the liquid version of water. Now, let's see if this works.
Atoms that make up a water molecule are in a constant tug of war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
I mean, think about when you put a pan on the stove and you want to boil water in it. You know, when you turn the heat on, it takes a little while before the water boils. What you're doing there is adding enough energy into the water to break these hydrogen bonds. They break, they reform, they break again and reform. And this is what you see when the water is, you know, coming to a full boil, as the bubbles are coming up and the water, the bonds are breaking and forming, breaking and forming. And so now your water is, you know, you raise the temperature to 100 degrees Celsius or 212 degrees Fahrenheit to get to boiling. And it takes a few minutes. It isn't instantaneous. So, because you're constantly breaking these bonds and reforming them. So fortunately for us, they are very weak bonds, but they form very easily. Okay. Okay, there we go. Now there is one more type of bond. You know, so we've got ionic bonds. You see it in those are in salts. We have covalent bonds. Most of our molecules in our bodies are going to be covalent bonded. we have hydrogen bonds holding our water molecules together. And we'll see hydrogen bonds help also with the shape of some of the large molecules. The shape of our DNA structure, the double helix of our DNA, that twisted shape, a lot of that has to do with hydrogen bonds too. And there's one more type of attraction here. It's called van der Waals. Van der Waals attraction occurs when you have nonpolar molecules. It isn't like a water molecule. Van der Waals attraction is when you have two molecules very close together, and molecules are always in motion. They're always moving their atoms around inside the molecule. And as they move around, if you have two molecules in close attraction to one another, if at some point you move, the molecule moves around and you create a slight negative charge on one molecule and a slight positive charge on another molecule, the molecules will be attracted together. And then it breaks apart. And then it forms again, it breaks apart. And so this is a very, very weak bond. Why do we care about van der Waals attraction? Van der Waals attraction is what we see when we look at fat, plant fat or animal fat. Plant fat in like Crisco shortening, for example, or margarine or something along those lines, is held together by van der Waals attraction. There is a very slight attraction between the fat molecules that breaks and forms and breaks and forms. Now, so we call it a solid fat. Animal fat is a solid fat because of the van der Waals attraction. The way the fat molecules are put together, they are in long chains that are very close together, in usually reasonably close approximation to straight lines. And so as the atoms move around, they create slight positive and negative charges, and they attract each other and they're solid. Plant fats that are naturally occurring plant fats are oils, like corn oil and soybean oil and olive oil and stuff like that. Those are oils, and they have distinct bends in their fats, and that keeps them from forming these solids. So oils don't have van der Waals attraction, but the solid fats do. So if you see, if you're in the store and you see the whole section of the corn oils and the olive oils and stuff, the reason they're all liquid is because there is no van der Waals attraction yet. When you look at the butters and the margarines and the shortenings, you do have van der Waals attraction. That's why they're solid. Even though the shortenings, the Crisco, and the margarines all come from plants, they've been artificially solidified. Nothing wrong with how they've done it. It's just they have created artificial solids. Anyway, van der Waals attraction. We see it in the solid fats, whether it's plant or animal based. That's about the only place that we readily see it. Okay. So let's talk a little bit about the chemical reactions that are taking place. We have chemical reactions going on in our bodies all the time. We measure that. We refer to our metabolic rate in our bodies. How fast are we breaking down foods? How fast are we breaking down breakfast? Or what we eat next, or how are we breaking down the calories from your Dr. Pepper or your drink, or whatever else I might have missed. It doesn't matter. I don't, but how fast do we break it down? That's our metabolic rate. Chemical reactions take place in our bodies all the time. We have reactants and we have products. We always have reactants. We always have products. The food that we eat or drink become the reactants, and the products are what we have left over after the reaction has taken place. Most food ends up as carbon dioxide and water as the products, and a release of energy. So when we eat something, we get a release of energy, and we ultimately end up with nothing more than carbon dioxide and the formation of water. Now, we do like to keep our reactions balanced so that the amount of energy produced is based on the amount of energy stored, and that, what we started with, we end up, at least number-wise, we end up with what we started with. Now, when we look at a molecule, we write it out in its molecular formula. Like H2O is the molecular formula for water. We all know that. And this is H2O. Yeah. 2 hydrogens, 1 oxygen. That's the molecular formula for water. Sugar, glucose. The formula for glucose is 6 carbons, 12 hydrogens, 6 oxygens, C6H12O6. That is the formula for glucose. All it is, it represents the bonding, the covalent bonding between the carbon atoms, the hydrogen atoms, and the oxygen atoms, even ionic bonds like sodium chloride, NaCl. Na is sodium, Cl is chlorine. That's the molecular formula for salt. So we show how, the formula shows you the atoms involved, the elements involved, and how many do we have. Yeah. In sodium chloride, it's 1 sodium, 1 chlorine. Water, it's 2 hydrogens, 1 oxygen. And in glucose, it's 6 carbons, 12 hydrogens, and 6 oxygens. And those are consistent.
Does the order in which you list the element matter?
Not really. It's just out of convenience, I guess, that we list the carbons, generally list the carbons first. But it doesn't really matter because you could, it's still going to show you that you're still going to have the same number of atoms of each type. So, but I think the conventions are you always like list the carbon first. I guess you could have HOC if you wanted to, but Okay, types of chemical reactions. This is important for our bodies. We have what are known as a synthesis reaction, where we build things up from little things. A synthesis reaction is we take smaller atoms or smaller molecules and make big ones out of it. So the process is known as an anabolic reaction. We build things up. Anabolic reactions usually require energy. We take little things and turn them into big things. We take amino acids and turn them into proteins. We take glucose, simple sugar, and turn it into glycogen. We store it in our liver. It takes energy to do that. But then we have all that extra stored energy in here. When we are storing stuff, we are storing energy. So that is a synthesis reaction. All the proteins in our body are made through synthesis reactions. All the hair color, eye color, skin color, all the enzymes, all color in our eyes, all the most of the hormones are all put together through synthesis reactions. And we call it an anabolic or a building process. Second type is the decomposition reaction, otherwise known as the catabolic reaction. We break things down. If you eat a cheeseburger, you break, cheeseburger is hopefully mostly meat. Not plant-based. Well, it could be plant-based, I guess. But if there's, it really doesn't matter if there's protein involved here. If you eat something that's high in protein, fish, beef, chicken, dairy, eggs, whatever, different types of grains, you would break those proteins down into their individual components, the amino acids. You break them down into the smallest units possible so that then you can turn around and build it back up into a protein you want. You eat protein, and then our bodies take that protein, break it down, and turn it into the protein that we want. The amino acids aren't destroyed. The amino acids are rearranged to do what we want them to do. Or you you eat cereal full of starches, carbohydrates, and you break those starches down to simple sugar, to glucose, because glucose is the fuel of our bodies. And we have to get the energy we need, we have to get to the level of simple sugar, the glucose. So we take starch, we eat an apple, we eat a banana, we eat a bowl of cereal, we eat a donut, we eat some sort of bread or pasta product. That's all starchy material, large molecules of carbohydrates, and we break those down to simple sugars. That's a decomposition reaction. It also releases energy. Breaking down breaking down large molecules releases energy. Just like burning the gasoline in your car, you release energy. Powers the engine. You use your propane grill. You got stored energy in the propane tank. You fire up the grill. You're breaking the propane down ultimately to carbon dioxide and water, and you're releasing energy to cook your burgers. So any kind of catabolic reaction is going to give you a release of energy, and you're going to end up with smaller molecules afterwards. And then the third category are what we call the exchange reactions, where you are building up and breaking down at the same time. And so this is a process where, for example, the manufacture of proteins is a good example here. You're taking a protein, you're eating a protein, you're eating a piece of chicken, you're breaking the chicken protein down into its amino acids, and then you're taking those amino acids and building the new protein you want from that. So on one side of it, we're breaking it down, the other side, we're building it back up into a totally different protein. We're using the amino acids found in the chicken so that you can make a protein-based hormone instead. And we go back and forth like this all the time. Okay. Now, a good example, besides breaking down protein, is what's known as this exchange type reaction, is an oxidation reduction reaction. Oxidation is the release of electrons. It's the release of electrons and the release of energy. Every time you burn something up, every time you burn something, you are causing oxidation to take place. You have a fire pit and you throw some logs in the fire pit and they're burning. They're giving off heat and light and smoke, and ultimately carbon dioxide and water, because it always comes down to carbon dioxide and water, along with other trace ingredients, but it's always coming down to carbon dioxide and water. So when you oxidize something, you are releasing the electrons that were held together through covalent bonds in the wood. If you're burning a log, you're releasing those electrons. You're releasing the energy. That is oxidation. Now, because we have to stay balanced, those electrons that when we burn something, those electrons don't get to run free and go somewhere, go wherever they want to go. They're going to usually get grabbed by another molecule, another atom. Atoms will, grab these electrons. Without feeding this into the ground right now, the formula for cellular respiration: glucose, C6H12O6 plus 6 oxygens yields 6 carbon dioxides, 6 waters, and about 36 ATP. That is the formula that we follow, that our bodies follow to gain energy from what we eat. And it's all about moving electrons. Now, I'm not going to beat this into the ground right now because, you know, we'll talk about cellular respiration in chapter 24. But what all you need to remember about oxidation is that oxidation gives off electrons. And when you give off electrons, you release energy. When you gain electrons, you generally gain energy. Chemical reactions are one or two types. They're exergonic or endergonic. An exergonic reaction is the release of energy. This is an exergonic reaction. I'm releasing energy in the form of heat and light, and ultimately also giving off carbon dioxide and water. We had the potential energy has been converted to kinetic energy. There is now less potential energy in the match and in the chemicals at the head of the match than there were before. And this is a catabolic reaction. It's also an oxidation reaction. I've released electrons. That is an exergonic reaction. We release energy. An endergonic reaction requires energy to work. Exergonic reactions, at the end of an exergonic reaction, you have more potential energy than you started with. It is an anabolic reaction. You're building something up. Catabolic tears things down. If you're going to bake a cake and you mix up the flour and the sugar and the salt and the oil and the eggs, the flavoring, whatever else in there, and you mix it all up, you put it in the pan, put it inside the oven, and turn on the heat. That's always an important point. You're applying energy to the cake batter. 30 minutes later, you have a cake, more or less, that is completely different than the batter. Now, theoretically, you could take that batter, and even though you've broken the shape of the egg, theoretically, you could take that batter and still filter out the sugar and the flour and the water and the eggs, the oil, and everything else. You couldn't put the eggs back together, but you could at least filter it out. Now, but because you've applied heat to it, you cause a chemical change. You now have a cake that has stored potential energy in there more than you started with, because you have created chemical bonds have formed in the cake, so you have more available calories of energy in the cake than in individual components from the batter, and you used energy for that. You stored energy in the food, in the cake, and that energy came from the heat from the oven. So, because if you let that cake batter sit out in the pan, you know, it's not going to work. But if you apply heat to it from the oven, it will change. It will be built up into larger molecules of carbohydrates with lots of stored energy there. Exergonic reactions give off energy. When you turn on the heating elements in the oven, you're releasing energy there to bake the cake, and you're using up that energy and you're applying it to the cake batter. The cake batter takes that energy, builds larger molecules, stores energy in the covalent bonds. Now you have your finished product. So exergonic reactions and endergonic, we use these all the time. We use up energy to move, to walk, to talk, to go eat. And then we store energy in the foods we eat. We store excess energy in the form of glycogen in our liver or as fat, or we build up other large molecules like proteins. Now, chemical reactions in chemist land are reversible, but they don't work that way in our bodies, because our chemical reactions take place at such small concentrations that it's very hard to reverse that. But the other thing is, more importantly, when we have a chemical reaction, we usually use up the product right away. So we can't reverse the reaction because
It's not there to reverse.
it's not there to reverse. Thank you. We've used it up. If we take glucose and we oxidize it, we're going to release the energy stored in the glucose, and all we're going to have left is carbon dioxide and water. So we can't go backwards. So it'd be, if we could do that, if we could go backwards, we would be, we would have unlimited energy available to us all the time. Sort of like plants. Plants do have one big advantage. Plants photosynthesize and store up the energy from the sun in the form of starch. But they too take that starch then and oxidize it, just like animals do, just like humans do, to release the energy to continue to grow. So they have a complete closed loop. They capture energy from the sun, and then they store it, and then they use it, and they capture more energy, and they continue. They're like self-feeding themselves, if you will. So we can't. A chemist will tell you that every reaction is reversible, but we'll tell you that not in our bodies. So, and let's see. I can do one more slide here and then okay. Chemical reactions are driven by a number of properties. Temperature causes chemical reactions to go faster. Chemical reactions go faster at higher temperatures. If you increase the temperature, you're going to cause the molecules in a mixture or in a solution or wherever you're going to cause your molecules to move around faster. Your cake batter bakes because the molecules are moving faster. You get the reaction of forming the large molecules in the cake batter. The more you have of your reactants, the faster the reaction is going to occur. This is one of those rare occasions where if some is good, more is better. Because you add more to it and it reacts much faster. And size matters. The smaller the particle, the faster the reaction will take place. If you're going to make sweet tea, are you going to dump 10 pounds of sugar into granulated sugar into a container of hot tea, or are you going to drop a block of sugar into the hot tea? Which is going to dissolve faster, the powdered sugar or the block of sugar? The powdered sugar, right. The block of sugar will eventually dissolve, but it will take more time. The smaller the particle, the faster the things dissolve, the faster the things react. So we can affect the rate of reaction by temperature and by concentration and by size, or we can use a catalyst. A catalyst in our bodies allow reactions to go rapidly. See, we have a problem. First of all, starting from particle size, we're dealing with very, very tiny particles, but we're not dealing with very many of them. So the size is small and the concentration is very small. And we're also sort of stuck. We can only operate at 37 degrees C or 98.6. We can't heat up our bodies to make our reactions go faster. We just can't do it. So a catalyst allows us to, a chemical reaction in our body to go faster, even though we can't raise the temperature, even though we can't increase the concentration, and we're already dealing with very, very tiny particles. So, okay, that is a great place to stop. And hey, Monday, I guess we won't have class till Monday. So we'll continue on with this. The lab tests will start next week on Tuesday. It will deal with the microscope and the tissues and diffusion and osmosis and mitosis and cell division. So when we talk about the skull in lab today and tomorrow, that's on the next test. Okay, and let me get you out of here now. So